everybody. My name is Isaac Montoya, and I am the Director of Marketing here at Upsite Technologies. I would like to thank you all for joining us here today for the fourth and final week of our 5th Annual Airflow Management Awareness Month. I'll be joined here shortly by Dean Boyle, the CEO of EchoSense, and Dr. Stu Redshaw, CTO of EchoSense, who will be headlining today's webinar. I will also be joined by Lars Strong, Senior Engineer and Company Science Officer here at Upsite Technologies, who will give a brief introduction for today's presentation. But before I pass it off, I'd like to go over a couple housekeeping items. So everybody will be muted for the duration of the webinar, just to block out any background noises. But we do encourage you to ask as many questions as you would like. And to do so, you'll notice that there is a Q&A module located at either the bottom of your screen or at the top of your screen, where you can submit questions throughout the duration of the webinar. So please feel free to ask as many as you would like, and we'll get to that in the Q&A portion at the end of today's webinar. If you happen to have any technical difficulties as far as audio or video, please feel free to shoot me a chat through the chat module, and I will try to get that resolved as quickly as possible for you. So, as I mentioned, this is week 4 of our annual Airflow Management Awareness Month. In week 1, Lars Strong spoke on airflow management best practices and cooling optimization. In week 2, Bill Clayman, the Executive Vice President of Digital Solutions at Switch, discussed how to recruit and retain the next generation of data center professionals. In week 3, Mark Acton, who is an independent consultant and non-executive director at EchoSense, gave a great overview of the data center standards landscape, both nationally and internationally. If you happen to miss any of those presentations and would like to see them, they are available on demand, and we are happy to provide a link for you to watch those later on in this webinar or in the follow-up email. Just send us a chat if you're interested in taking a look at those. And finally, today, Dean and Stu will discuss how emerging software systems are utilizing artificial intelligence and machine learning to remove thermal risk and optimize the cooling infrastructure of mission-critical facilities. So, without further ado, I'm going to pass this off to Lars for a brief introduction for today's presentation.
Excellent. Thank you, Isaac. We are really excited to have both Dean Boyle and Dr. Stu Redshaw joining us today to discuss this important and really potentially valuable topic to you. For those of you who don't know, Dean and Stu co-founded the company EchoSense with a mission to help data center managers take control of their thermal risk while improving both cooling efficiency and capacity. So not a light goal there, and they've really attacked that. Dean has vast experience on the technical services side of the business, where he is focused on delivering energy savings in data center and telecommunications facilities. And Stu holds a doctorate in heat transfer and thermodynamics from Nottingham University in the UK, and is a specialist in energy efficiency and heat transfer within the HVAC, building services, facility management, and utilities sectors. Together, Dean and Stu bring over 25 years of thermal expertise to this discussion. Their EchoSense solution has been deployed in over 350 data centers and is based on artificial intelligence and machine learning algorithms. So it goes without saying that Dean and Stu bring a wealth of knowledge on the topic at hand. I know they'll discuss this point in more detail later in the presentation, but I want to point out and want to touch on the fact that AI and machine learning have become buzzwords in their industry. They've been thrown around a lot as solutions to almost every issue in the data center, and to no one's surprise, have come up somewhat short on most of those perceived promises. And at the risk of making too bold a statement, I believe the place for this technology to really shine is in the airflow management and cooling optimization realms of the data center. As I've mentioned many times in my own presentations, cooling optimization is an iterative process, and it starts with improving the airflow management in the computer room, which creates the opportunity to make adjustments to cooling controls and set points where you can then realize energy savings. The challenge is that air is invisible, and that makes it difficult to see what's going on. So it can be hard to identify locations of excess cooling and locations of deficient cooling, and to know what adjustments to make. Um, of course, monitoring the thermal performance of the computer room with temperature and relative humidity sensors is the first step to identifying those, those cooling dynamics and the opportunities for improvement. But making sense of that data is where there often is a challenge and where people often run into stumbling blocks. So this is where AI and machine learning software can come into play. And through the visualization of the thermal performance of the data center and the analyzing of that data, these types of software can take the mystery out, or simply the uncertainty out of the process of optimizing the cooling infrastructure. And after all, at the end of the day, we're all working to provide the highest possible uptime at the highest possible efficiency, or in other words, the lowest possible operating cost. So AI and machine learning can be the missing piece of this puzzle to achieve these goals. So I'm really excited to have this presentation done by Dean and Stu today, and hopefully it brings up a lot of questions for you. As Isaac said, please type those in as we're going through, and we'll get to as many as we can at the end. So with that, I'd like to pass it over to Dean and Stu to go into much more detail.
Thanks, Lars. Thanks, Isaac, also for the introduction. So first of all, hello to everybody on the call. Thanks also to Upsite for the opportunity to take part in their annual Airflow Awareness Month. We are very glad to take part in this. And finally, thanks to everybody on the call. I know it's a challenging time at the moment, so really do appreciate your time, and I hope the session is worth your time. So just on the agenda slide that I've got up there, I'm going to go through some things that are very well known in our space. So I know I'm preaching to the converted, but we'll go through some of the background to data center challenges, some of the things that Lars has just mentioned. We'll go through some of the analysis that we found when we've been looking at data centers and optimizing data centers. We will look at some of the typical tool sets that are used in the DC space. We'll obviously cover some of the general background AI, machine learning space in the data centers. We'll go through our typical optimization approach, the way we've tackled it, the way we've used the tools. There are lots of different types of tools available, which I will cover today. Then I think the most pertinent bit really is the case studies. So as Lars was saying, there's lots of talk, lots of hype, but really we wanted just to show you. Now there's obviously a spin of some of the ways that our software works and the ways that our software can help alleviate some of those problems, but some real tangible case studies about where this type of technology can help, how it can identify issues, how it can resolve challenges, and then give you some ongoing tools for further down the line. Then we're getting into some of the wrap up. So I will recap on some of the key takeaways, hopefully, and then we will gladly take questions at the end. So hopefully that is what you've all signed up for. If I just click through. So again, I realise some of these stats are well known to most of the folks on the call, but still worth going through it again, just to set more of the background to why we do what we do and the challenges that we face. So generally accepted challenges in the data center space, there's four: risk, capacity, and energy being the key one. So risk, thermal issues generally account for about a third of unplanned outages in the DC space. We have analyzed a lot of data sets. So as Lars was saying, we've worked in circa 300-400 data center optimization projects. So seen countless numbers of data sets for risk projects, for optimization projects, for capacity release projects. And typically across those vast numbers of data sets, a massive over provision of cooling, but the cooling utilization is only running at about 38%. Another quite interesting stat is, and again, it's tens and tens of thousands of racks that we're either monitoring or we've been involved in as part of optimization projects and cooling projects. But generally, 15% of racks run outside of the ASHRAE guidelines for inlet temperatures, which obviously then leads to downstream thermal issues and outages potentially. Now, again, I realize this is a very, very well-known stat, and there are hundreds of this type of stat banded about in the industry, but typically 35% of total mains incoming in a data center facility is used upon on cooling, and which accounts to, or equivalent of about 73% of the non-IT load. There are lots of systems that are incumbent in a data center. I'm going to touch on some of the major vertical products in the sector shortly, but they are there, they're well understood, there's great use cases for them, but they're not typically, all of them, not typically good at spotting point thermal challenges or spotting trends at a very granular level. So I'll find those numbers on there generally based on our findings, but we have also found that the number of stats that are published in the industry, there's a pretty good correlation between industry stats and what we've found with our own analysis over fairly substantial data sets. At the heart of this, obviously, is good optimization. So good optimization helps resolve all of those, but the topic of today's session is mainly around risk. So that is, of course, where we're focusing. So just following on really from some of the introductory words from Lars, and I've titled it Reviewing the Hype. So it's used in all manner of life these days, artificial intelligence, machine learning, buzzwords that have made the rounds throughout the industry, throughout our industry, our DC industry as a panacea to many DC and IT related issues. You could also throw into the mix other phrases, words, so deep learning, neural networks, obviously nuances between all of those words, but generally the same type of sentiment. I think it's probably fair to say, and Lars touched on this, they probably have come up short in terms of the marketing hype and the perceived promise of what they're going to deliver. But from our very niche world that we live in, optimization, airflow, cooling, thermal, we feel, I mean, we're a vendor, so ultimately, of course, it's our livelihood, but we feel that this is where machine learning, artificial intelligence can really come into its own and deliver proper, tangible benefits. And hopefully you'll agree when we show you some of the case studies later. Utilizing the technology, of course, it is going to flag up airflow challenges, spot trends in cooling unit performance, show that the correlation between cooling unit performance and rack inlet temperatures, and then marrying up of power as well, and basically trying to de-risk the white space and take any kind of thermal challenge away. Whilst those things are all well and good and using AI, machine learning to drive efficiency and drive out risk, they fundamentally those challenges have been around for a while, and obviously there are software systems which claim or do actually address some of those. But I think it's fair to say, so point 4 on there, it really is some of the latest technologies. So modern browsers, the power of the browser, latest programming techniques, gaming technologies to support the visualization of software, and absolutely the scalable cloud infrastructure. So we run on a very well-known cloud infrastructure. It gives us instant scalability across the globe, high levels of resiliency, security. And the other thing which is absolutely vital to AI is sensor technologies. So for us, we're always looking for more granular data sets, lots and lots of data sets. And again, new sensor technologies, IoT technologies, IoT protocols, they really do facilitate AI and machine learning. And obviously the power of the cloud and the massive data sets that you can crunch using the processing power are phenomenal and almost unlimited. So what they actually do, they allow you to make or they support instant optimization decisions, which is at the heart of everything that we do and the things that we get involved in. So I suppose the last point, so yes, reducing risk is a fundamental requirement, and again, just the way we tackle it, there are lots of things that good optimization, good sensible optimization does. The headline is usually energy, so save energy or release stranded capacity, but really it's all about removing risk, and we always look at risk as the driver, and then it's capacity or energy as the payback. And as I say, the one that gets the headline, and obviously real-time analytics through the power of AI can support that those goals. So trying not to make this too heavily biased towards our own product, I just wanted to look at and have a look at the merits, the pros and cons of the different, I guess, vertical product sets in our industry. Again, these are very well known in the industry, and I realise the expertise on the call. So they've all got their own very, very solid individual use cases, well understood in the industry, and they usually address their very specific customer requirements and are very good at it. And we absolutely don't claim to take part in some of the things that those systems resolve. So just working through left to right, obviously BMS is a absolutely crucial and mission critical environment platform in every single data center. Generally designed to control and manage mission critical infrastructure and generally alert on hard faults or SLA breaches. We find that some of those are too late. Obviously, it's very reactive, not very proactive, not so great at spotting trends in our experience, and potentially costly. But at the heart of every DC is a good BMS system. And generally, we work very well with BMS systems. Just as I'm going through, and it's obviously not an exhaustive list, I've just tried to put a sample of the types of customers, types of suppliers that play in these verticals. A number of them, people like Schneider, obviously play it across a number of those verticals. As I'm going through them, as well as I look at some of the names, I'll also touch on where some of those also claim to have some artificial intelligence, machine learning capabilities. Schneider, they have done some, again, quite well publicized data center management as a service, and they partnered with IBM's Watson, and that's mainly around, less so on risk and more for IT capacity management and a little bit of M&E capacity management, but they definitely have got claims to have some artificial intelligence capabilities. Moving along, the next one is electrical power management systems and EMS systems used interchangeably. So very similar to BMS systems, but obviously very focused on the electrical side of it, often combined and often the same type of offering. Then you get into, I guess, some of the analytics type platforms. So CFD definitely has analytics, of course, and fantastic for new build, new design, where you've got no base metrics to work from, but theoretical and very little. There's some of it coming, but very little claims on real-time skills and capabilities for real-time optimization. If I just jump to the right, you get into the DSIM and the asset management, and again, extremely well documented, good and bad for DSIM type systems. Sometimes get a bad press, and sometimes that's warranted, sometimes not so. They are largely driven, so in our world, we're focused on the M&E side of it, and particularly on the cooling thermal side, but DSIM systems typically have arisen and are based on the IT side of the equation. Very little focus, to be fair, on the M&E side. Of course, that happens, and certainly people like Schneider have a very powerful M&E product set, but generally they are IT focused. Normally they are very capable and absolutely capable of doing very granular reporting, so temperature thresholds, very granular at the temperature at the rack level, but often very, very costly. And I think, again, it's fair to say that DSIM projects are very rarely driven from the M&E teams, and they are absolutely the reserve, usually, of very large corporates who have the budgets. Manpower is a very good one, so usually need quite substantial manpower teams to manage them, and large implementation teams are very difficult to administer usually. There are some AI machine learning claims from the DSIM world. So a couple that I know about and seen a little bit of experience of is Nlight. So Nlight have a capability, again, mainly focused on the IT side of it, server workload optimization, IT capacity management. And there's I think it's a Canadian company called Maya, are also very strong in that area. Then back to the one highlighted, again, obviously this is the type of arena that we fit in, but there are other types of systems, Vigilant to name but one, where machine learning, latest technologies, crunching in multiple data sets using the processing power of the cloud. There are a number of well-publicized initiatives, mainly from Google, a little bit from Huawei, and Google have actually done quite a bit that's in the public domain, where they have used their own artificial intelligence, machine learning algorithms to drive fairly substantial costs across their own internal DCs. I've seen various claims, but somewhere between 30 and 40% annual cooling energy from marrying up server inlet temperatures, cooling unit performance, server utilization, and swapping workloads around. So some very, very impressive claims there. And again, they've got their own DeepMind AI technology. Not a lot in the commercial world. So Huawei and Google both use it for their own facilities. Whilst there is some in the IT workload, there's very few vendors that actually claim to have anything to work AI type capabilities in the M&E space. Just a little bit more on that. So I won't spend too much time in this. And of course, there are nuances, exceptions, depending on what's your flavor or what you're trying to argue. But it's just basically obviously a tick box exercise to show where we think some of those vertical product types, where they excel and where they really major on their target audiences. I've grayed out ones that are not really specific to risk. So a lot of those platforms do other things than just risk, and they have a particular reason for being, and their core product or their core offering is not driven by the risk side of it. So that really is where I was going to stop. And now I was going to hand over to Stu, who will cover our recommended approach to optimization, how we use the technology, and give you some real tangible examples of where artificial intelligence, machine learning, and analytics can spot thermal risk, spot trends, and hopefully stop potential outages. Over to you, Stu.
Great. Thanks, Dean. And thanks, Upsite, for hosting us on this call. What I'd like to cover over the next few minutes is where artificial intelligence and machine learning analytics have proven to be effective in benefiting the data center industry. I'm going to try and be as agnostic as possible, and there are many different approaches. But here in EchoSense, we've been working on a unique approach that includes a selection of analytical tools to solve some industry challenges around efficiency, capacity, space, and cooling. One thing I wanted to put in here as well is about our approach normally and generally is underpinned by industry standards from bodies such as ASHRAE and ETSI and others. But where the AI is concerned, in all its flavors, the standards industry is still learning. This provides great freedom for us to innovate new solutions, which is really helpful, but also suggests that there are risks as well as benefits that need to be considered. And I'm going to try and describe some of these issues as I see them later on. Okay, so our approach is based on 5 simple blocks. We've got to gather some data, we've got to visualize the data, perform some analytics, and then deliver that and repeat. Not all of the vendors in this space are following those 5 steps, but if I go through them step by step, I'll try and highlight what others are doing where I can. Okay, so step 1, and I think all the analytics platforms will agree with this. You've got to gather as much data as you economically can for your application. It's absolutely vital, and everyone will be agreed on that. Exactly how much data you can gather economically is another question, and each different application will have a different ROI on the data you gather, but everyone's agreeing the more data that you can put in there to process, the better the output's going to be. The data itself could come from all kinds of different sources. So it could be custom sensors, something that we specialize in. It could be client sources from their own data. It could be integrating with the cooling machines or the IT systems in the data center itself. It could be public information. It could be weather data from APIs. It could be survey information, all sorts. But broadly speaking, the data can be divided into 2 particular categories. There's a high quality data, which can be validated and verified, and you know where it came from, and you know it's calibrated, and you know what you can do with it. And then there are low quality data sources. Both types of data have uses, but in our application, we tend to be more focused on the high quality data sources, which is one of the reasons why we've had to develop our own series of sensors for that purpose.
And just to reiterate, again, it's that cost of sensoring, and we talked about some of the enablers early doors, so cloud, sensors, and really it's that having access to those very, very granular data sets, latest hardware technologies, latest IoT technologies and protocols, actually makes this a reality. So it gives you the data granularity requirements that you need at a sensible cost.
Okay, second step. So there are two schools of thought on this aspect, so the visualization. So for some players in the market that are using AI, one of the fundamental purposes of it is to remove the human from any kind of involvement in the system, in the process. So there is really no need to worry about the human interaction component of this. You don't really need to see the data if you're processing vast amounts of information to produce a control algorithm, for example. But for us, the opposite is completely true. We want to provide the best sources of data possible and present that data in an intuitive fashion to support the human users in making decisions. So we believe that involving the humans allows for a very special step that's often neglected in AI applications. We want the user to actually learn and develop while interacting from the software, rather than have a distinct black box where things are happening that no one can really penetrate or understand. Both approaches are valid, and we'll talk a bit more about both in a second, but our particular specialty is definitely the visualization of data that comes from the AI.
Yeah, and I think we'd also say that one of the reasons there's some perhaps slightly negative press about some of the types of DC software systems available in the market is they're not particularly intuitive or simple to use or engaging to use. They are not particularly available to or usable for a different mix of audiences. So, and it's always one of the challenges that I think modern systems need to overcome. So you need to very specialist skilled data sets in power, cooling, thermal, how they interact and the learnings from that, but make it's a waste of time if it's not viewable and understandable in a nice, simple manner, and it's not you can't engage with it across quite a wide range of audience in the customer. So that, again, that's the aim of these systems.
Okay, so now we can do some analysis. So very roughly, for the purposes of this discussion, we're going to divide the types of AI that you can do into two broad categories. So these are types where unsupervised learning happens, and then obviously there's a type where supervised learning happens. So the unsupervised learning algorithms are the ones that are normally associated with AI in its pure sense, and they're the neural networks. And they're available systems that can be trained to learn for patterns that deliver a particular positive or negative outcome. So in our industry, that's the classic one, where an optimization goal could be for minimizing cooling power, for example, given some limiting constraints such as rack temperatures. And we ourselves have got a little bit of experience with deep learning algorithms of this type, where we've used them to process object recognition data. So to process numerous thousands and thousands of pictures of frames and racks, and then training an AI engine to process that that information to be able to select automatically when a picture may be of a rack rather than a door or a wall or other things. And the unsupervised learning engines are fantastic at this. One of the great benefits we've got in our industry at the moment for the use of unsupervised learning is coming from the autonomous vehicle sector, where billions of pounds are being invested every year developing that kind of technology, where processing speeds are incredibly rapid. And there's a lot of opportunity to take technology from that sector to try and put it into our sector, where obviously investment and development is much smaller, but we have a use case that's much easier to understand. And this is one of the areas that we'll be looking at closely in the coming years to help us with our how to populate and how to survey rooms more rapidly, how to build 3D models quickly based on survey data. These kinds of tools can be really helpful. So the second type of algorithm, the opposite type, of course, is the supervised learning type. So in our case, we're normally more interested in the supervised learning techniques like machine learning, where the software uses formal engineering maths to interpret huge volumes of data with the goal of learning insights from the data and then communicating these insights to our users. basically we want the machine to advise the user and provide guidance on what to do next. But because it's supervised machine learning that we're involved in, we have a great deal of influence over the fundamental maths that goes into the algorithms. So we can control it, we can make sure that the calculations are based upon industry standards rather than unsupervised learning, where machines could be picking up on any kind of data set from any source that just happens to statistically match the goal that you're trying to achieve. So delivery. So as mentioned, there are two schools of thought on delivery, and in the automatic AI engine, which is delivering a control strategy, for example, you may keep this hidden from view. In fact, you may even restrict humans from being able to view what's going on, because it's not there isn't an easy way to understand how an AI engine is delivering the functionality that it does. But for us, it's all about providing deep insight and actionable advice to any end user looking to improve their site performance. We really want the human to remain the executive agent in our approach. So the types of procedures that we can deliver are very broad. So because the tools deliver insight, the ways that they could be used are as broad and as wide as you can possibly imagine. And in some of the case studies, I'll just give a flavor of how it can be used in lots of different ways. Okay. Yeah, and the repeat, that's because we're focused on empowering users of our tools. It's vital that small steps are taken frequently. So issues where they are detected, and we'll definitely show you a few of those in a moment, should be obvious, but routine action should be interesting and informative and not seen as time consuming. If we're successful in building our analytical tools, it should make operating data centers easier, simpler, and more profitable. And hopefully we'll also be able to show you a little bit later about what the next generation of user interface could look like that could completely revolutionize the way that users and humans are interacting with the physical assets in data centers.
Yeah, I think it's just important to say, just to repeat some of that stuff on there, that it's more than just a one-off approach. So whilst in the past some customers have asked to do a one-off optimization, and of course we can help and solve the immediate challenge at hand, but the dynamic nature of the IT environment, the dynamic nature of changing weather conditions, cooling unit performance, it absolutely has to be an ongoing process, and optimization really does need to be built into the heart of operational processes for the data center.
Great. So case studies. So we've got a few case studies to go through, and what we're going to do, we're going to roll through them all fairly quickly and look at them from a pure engineering perspective and quickly understand what's going on. How did the analytics provide insight that was important to the customer, valuable in order to get these engineering problems fixed? But then at the end of that, we'll go back and look at them again, and I'll slightly change the approach and in the way of looking at these particular case studies to explain more about the AI part of that. So if we could roll a movie, please. Here we go. This is a simple one to start, if you like. So if you could. Okay, so in this example, we've got a corner view of a data center, if you like, in a 3D piece of software to show us that. And the colors of the rack are our temperatures. So obviously we want to try and maintain a steady green, but we've got some colds in there and a mixture of yellows and ambers as they're approaching 80 degrees Fahrenheit, where they would suddenly hit a red, which is a breach of an SLA. The cooling machines around the edge of the room are also showing us the supply and return temperature, also with a color spectrum on that as well. Now, over a period of time, the software's learned the behavior of this room. So even though there's quite a lot of variation in the rack temperatures in this room, its behavior is normal. So there's opportunity for optimization there for sure, but the behavior from an AI perspective is normal. So it's looking at that and it's learned over a period of time that that's steady state, that's normal. So then we allow time to continue a little bit.
So just one or two technical issues there. The video has moved forward. Let me just go back and play that again. Sorry about this, folks.
Just jump us in.
Get there in 2 seconds. Challenge of technology and video presentation.
Yeah, I won't pause it again. We'll just keep rolling. So we have the steady state condition. The AI engine's learned the room. It's understanding the behavior of the cooling systems in there. Later, the software's detected, and it's quite apparent because we're seeing at the analysis data that the output from one of the cooling machines is becoming variable. So its behavior has changed, even though the rack temperatures haven't significantly changed. So it's at that time that the software is starting to issue warnings well ahead of any issue. Then over time, situation degrades even further, and the cooling system in that corner actually fails, leading to an SLA breach and a fault. Up until that point, there were no alerts triggered by the BMS sensors until the very last moment. So this kind of output's given potentially days of additional warning time to show that something strange is happening to the cooling machine. And it allows everybody to get in place a fix prior to there being an outage. The software also gives us the opportunity to really target the fix that's necessary in order to get the site back to normal. So the refrigeration or the maintenance crews are able to forensically look at the historical data in order to target their actions for the fix and then get it back to the steady state operation as it was previously. So that's the first simple case study, just to show you an example of the pre-warning that you can get because you have this historical behavior known. Okay, you'll be glad that's the only movie we have. So these ones are all fixed slides, so they're a bit simpler to navigate. So what we'll do, we'll start on the left-hand side of the slide. And in this particular case, we're looking at a relatively small financial institution with a very robust configuration in there. So it's at least a 2n+2 configuration, water-cooled system, absolutely dedicated to the robust solution, so it must not fail. And then picking up in the software again, similar kind of predictive change, and it's obvious when you look at the color on the racks, but this is the kind of output that's coming from the software, that the behavior is changing in some of the units long before there's any impact on the room. And then over time, that develops until we're seeing virtually every single rack in the room being impacted by a change in behavior of, in this case, 3 of the air handling units. So that's allowed a maintenance event to take place to get that site fixed and resolved and put back to normal far quicker than, or in fact, well ahead of any other solution that could have done that. As it turned out, the solution that the problem with these particular units was they'd undergone a maintenance which had reverted their set points to factory set point, but it's only 2 degrees different from the normal operating condition. And of course, under those conditions, there was no fault from those units. They were working perfectly normally. So it was a really helpful output for our customer to see that ahead of time before any SLA breaches happened. Okay, next one. So this is a slightly different view from on the left-hand side from the software, where we're able to also build into the analytics a power view. So we have here all of the power capacities and usage rates for each of the IT systems is placed on the 3D floor. So we can incorporate that into our analytics. In the center, we're looking at a very important piece of the analytics engine, which is the zones of influence. And the zones of influence allows us to associate each particular rack with the cooling unit that supplies it. And this is a time series piece of analysis that allows over a significant period of time the temperature variations of each particular rack to be located and associated with each particular air handling unit. And they form patterns that tell us the relationships. And we use this extensively to work out each particular zone, how much load there is in each zone associated with each air handling unit. And is a very important day-to-day use case for the software to be able to do those two things. So incorporating the zone of influence where each particular air handling unit has an impact, and also looking at the quantity of power that's being used in that location is a fundamental part of our solution. How it's delivered on a day-to-day basis for customers, once you've got those two tools working together, you're able to then do instantaneous scenario planning using the output from the analytics. So for example, on a new data center on the right-hand side, where we're building a new rack or a series of racks are going to go in on an upgrade to a site, it's very quick to be able to move objects around in the room almost in a pick and place fashion and get an instantaneous accept or reject in terms of the capacity of the floor to be able to handle that new heat load, which is a very important feature. Also, we're able to use the same kind of analytics almost in reverse to fail or simulate the failure of an air handling unit and then recalculate the zone of influence and see how that impacts in terms of resilience. Okay. So another example now, building again, so bringing all these pieces together. In this example, we've got a really heavily loaded site where the customer has really pushed the envelope of what they can get in there in terms of customer. And you can see that in the middle of the middle image where the power view is shown, that the very tall green objects are telling us that those particular racks are very highly loaded. So you can see the distribution of power across the floor is very uneven, but there's a lot of power being utilized and a lot of heat rejected on the part of the room that's nearest us as we look at this view. Then classically in these case studies, over a period of time, the learned behavior goes into the software, and then there is a change. And the change in this case is the degradation in performance of one of the air handling units that just happens to be associated with the worst possible place in the room, where it's very highly loaded and where the overall resilience is quite low anyway. So the same kind of output, that building all these things together allows us to give true insights and very early warning to customers when there's potential problems are coming. And this is particularly helpful in these sorts of applications where time is critical because the loadings are quite significant. There's not a lot of margin for error in these kinds of applications. Okay, last case study now. So in this site, we've got a regional site, a very quiet site with a large amount of cooling. It's lowly populated, not a lot happens in there. It's in steady state for a very long period of time. And then we notice in the software that periodically there is a huge change in the overall temperature of the room. And the software highlights this to us, that for some reason, periodically, 3 of the units in this data center are standing down. And we can see this routine behavior start to develop in the software, that quarterly, this kind of behavior has been happening. As it turns out, in this case, it's a customer site where associated with this quarterly event was also a generator test that had been going on. And later the analysis of the issue found out that the BMS had a loop into 3 of the units that were standing down in the event of a power outage, a legacy piece of configuration that had been forgotten about, but was quickly able to be removed once it was seen in the software. So those are all the case studies from a pure engineering perspective. And what I wanted to do now is go back up to the first slide of case study. And I just wanted to talk about that from a slightly different perspective that's particularly pertinent to machine learning and artificial intelligence. So I expect everybody's heard of Alan Turing. And Alan Turing in the 1940s and 1950s devised a special kind of test which could be used to test where AI systems are operating. And it was an interview technique where an individual would ask questions of a machine or a person, and you'd have to decide if it was a machine that was answering the questions. And it took a number of years to be able to do it, but he predicted that ultimately it would be impossible to tell the difference between the machine and the person. Well, what I want to do is do that here, but from the perspective of a rack or an air handling unit, but use the same output from the software, the same tools that we've got that are presenting this information, but do it from the perspective of asking a question of the rack. So if, for example, in this particular case, hopefully you can see my mouse, we ask any particular rack in this room, what is your condition at the moment? It would be able to tell us by analyzing all of the information extracted from the analysis that its current condition is okay, and it was okay yesterday, I'm very stable. The air handling unit that supplies me with air is operating normally, I can see he's working, and I can also see that if the air handler that supplies me fails, the one next to it has more than enough capacity to pick up. And this is one of the tests of a good AI system, that those kinds of insights could easily be provided. If we go to the next case study, that's the one after that, we could ask some of the same questions of a rack in this particular room. So we could ask any particular rack a question. So we will pick one right in the middle of the room and ask the same question. What is your condition? How are you feeling? And this particular rack would tell us, yeah, I'm in a good condition. I'm slightly colder than I should be. And historically, I've been in this condition for a while. My air handler is working well. He's operating normally. And I know if he fails, there's another one that I'll be able to be cooled by. So it's feeling confident. It almost has an anthropomorphic mechanism to be able to communicate to us as viewers of the software. And it's one of the ways of getting insights from the software that we're getting really excited about. The idea that you don't necessarily have to look at a dashboard of information and interpret that, but you could actually go to a device in a cyber-physical sense and interrogate it for the insight and ask it how it's been performing and how it feels about the environment in which it's working. Does it feel that the environment is too hot, too cold, or even that it might be risky? Does he feel that there is any risk there? Does he feel that there's any problem? And these are the kinds of applications that we're working on at the moment to be able to really exploit the analytics that we have and present that information in a really breakthrough ways, new ways of delivering that kind of functionality. Okay.
Thanks, Hugh. Just a few key takeaways. We're just running a few minutes behind. I know we've done some of these to death, but granularity of data is absolutely required in machine learning AI systems to effectively drive out risk. Again, it's not because vendors like us want to sell lots and lots of hardware. It's because it's absolutely crucial that you have got that visibility and can effectively measure the effect of change. Tools must be easily usable, easy to visualize the issues, and engaging to work with, and particularly when you're supporting fairly complex optimization activities to try and de-risk it and to make it as simple and intuitive as possible. So model analytic systems, and there are a few available, can link the performance of cooling units to inlet temperatures on racks, take external factors in, as Stu said, weather data, power data, even to drive workloads, IT workloads, all geared obviously to reduce risk, but also to improve efficiency. A proactive approach to and visualizing early warnings is absolutely required to reduce risk rather than wait for a very typical reactive approach to hard faults. And I've mentioned it, optimization we think is vital. It's built into regular operations processes. Artificial intelligence, machine learning platforms will become the norm. They are absolutely on the way there. Some of them are there now. There are a few examples that I've mentioned. We're doing a lot of work. I know there's some other systems that are also doing some fairly exciting stuff, and there'll be a number of commercial offerings available. And it is obviously vital that people adopt these to drive risk out of environments. I think the biggest use for them, and obviously the crux of this presentation, is energy efficiency. Certainly in the M&E space is crucial. But that whole failure prediction and that workload management are the three key areas where we see artificial intelligence really being used. I think I just about wraps it up from the formal side of it. So again, just many thanks for listening, and over to Isaac.
All right, thanks, Dean. Thank you, Stu. Great job on this presentation. We've got quite a few questions coming in. For those of you who have not submitted them, please feel free to submit them now as we get started with answering them. So I'm actually going to jump ahead a little bit here. We had a question in regards to one of the case studies. So someone wants to know, what was the thermal rate of rise in the case study, the second to last, where the crack failed? How long before thermal impact to that zone of servers?
It was a fairly rapid one, but over a number of hours. So it had been indicating that over several days, it had been indicating that it might get to that point. So over several days, the warning message had been coming out, but then because it was following the variation in daily temperature slightly, that was impacting it as well. And then on the day when it finally breached, it was by the middle of the day it went over. So the total duration of that particular issue could have been a number of weeks, but ultimately it breached in a single day when it breached the SLA. Is that okay?
Yeah. Got it. Thank you. Let's move on to the next one. Many sites have redundancy on paper only, and cracked and standby cannot adequately affect another zone too far. Are you testing for true redundancy?
Yes, we are. So there's two elements to that. So there's a simulated test. So when a unit is stood down and removed entirely from the overall heat loads, and then you reconfigure the zones of influence to take up and pick up that heat load. But there's also the supporting the teams on the ground who actually undertake resilience testing and physically turn units off, and then providing them with the tools at the same time to monitor that activity in exactly the same way. So yeah, we'd like to think that we correctly look at those.
All right, thank you. Moving on to the next one. One of the challenges we see with the AI and machine learning research is how to deal when there isn't data available for the future scenario. How can your system confidently place new hardware, for example, laying out an entire cage for a new colo customer when there is no data available for the scenario to train the AI or machine learning algorithms?
Yeah, that's a great question. And I think that you nailed it in the question with the word confidence. So the way that we've done it is our confidence reduces in our prediction depending on the amount of new or the amount of change that we're building into the new scenario. So if it's a relatively small percentage of change, we'll be confident in our scenario's output, but it still has to be taken as indicative. But if the changes are larger, if it forms a greater percentage of the overall heat load or cooling capacity of a site, then our confidence will reduce. And we obviously indicate that in all of our calculations. So you get a confidence bar along with your accept, reject criteria.
All right, thank you. Is there a role for predicting and ranking rates of temperature rise following various types of HVAC impairment to help prioritize remediation?
Yes, I think so. So most of the analysis that we do is time series. So we are all of the important maths functions in our software use time series analysis, and we're looking at rates of change very carefully at a number of different scales, whether that's compressors kicking in and out on particular frequencies and other things. So time series is a vital part of what we do, and there are so many different applications of time series analysis. It would be hard to go through them all now.
All right, thank you. Let's move on to the next one. What is the rack sensor density that you suggest? Understandably, more is better, but at what cost?
So yeah, again, you've kind of answered it with part of the question. So we would always argue for lots and lots of data sets. The systems are built to accept lots of data sets, and as Stu mentioned, you have more confidence in the output, the greater the data sets and the more granularity of data. So, but I understand there is a commercial challenge, which is why and I don't want to keep referring to the stuff that we do, but we've done a lot of work on cost engineering to drive out the cost of sensors, and obviously some of the IoT technologies enable that. Also, I think good systems should really take into account different types of sensors as well, and integrate with whatever sensor points you've got, including perhaps raw sensor data or raw board temperatures from some servers. So whatever data sets you can get, feed it into the engine. But I think just to give a more succinct answer, we would recommend, in fact, we need one sensor on the inlet on every single rack, or a significant portion, so at least 80% of the racks. And also, we must be able to correlate for zones of influence and some of the deep machine learning algorithms. We also need the cooling duty sensors. But generally, they are not cost prohibitive. Again, easy for me to say, but I just know from some of the other systems as well, where it's the data is so valuable, you just want to make it very easy to put lots and lots of data sets in. So yeah, we would recommend one sensor. In fact, we must have one sensor on every single rack and cooling unit sensors.
All right, thank you. What is the experience with HPC data centers, especially with DCLC solutions?
So we've worked in all sorts of data centers, some a little bit of HPC type stuff, as a definition of HPC really. So some of the universities that we've worked in have some HPC environments. So we've worked on enterprise, classic end user sites, through to very big colos, wholesale scale, through to some HPC. I have to be honest, we haven't done a lot of it. So you're talking single digits of university type buildings that really do HPC. So beyond that, we've not done a lot, but I have to say we've not seen many issues. It's the same challenges, different types of environments, obviously different types of results, but generally it's the same type of environment, and you just get the mixed densities and different types of cooling unit that support that. So we've worked on most types of environment, and the systems generally, again, I can only really speak for hours, but the systems generally lend themselves pretty well, and they have to lend themselves pretty well to mixed environments.
All right, thank you. I think we have time for one more. If I have a rack or area of racks that remain in blue status, what recommendations would the AI system make to balance cooling?
It would be looking at the zone of influence. So it would rank all of the zones of influence and find out which particular zone was the most affected by low temperature. Then it would target an action to that zone. So the actions to that zone then could be a number of things. There could be adjustment to grills in that location, or it could be an adjustment to the set point of the air handling unit that feeds that zone, or it could even be a recommendation to turn that particular cooling unit in that zone into standby mode to allow it to be, that particular zone to be picked up by another cooling unit. So there's a whole series of actions that work through in the optimization phase to try and fix that cold rack.
And just to add to that again, just on balance, there are other types of systems that you would put in the same vertical as the EchoSense product set that would take that one step further, and they would make that automatic change. So the machine really is controlling, but you've lost that human auditability. So you can absolutely take it through to full autonomous control using these types of systems available today.
All right, thank you very much. I think that is all the time that we have, but Dean and Stu, it was great having you, great presentation. We really appreciate you joining us for our Airflow Management Awareness Month, and thank you to everybody who joined us both today as well as for our previous Airflow Management Awareness Month webinars. Dean, Stu, again, thank you so much. We're happy to have you.
Thank you.
Thanks, cheers.